Hello, y'all. Today we're going to be talking about four inductive inferences from chapter 8 and a little bit from sort of chapter 9, but we'll get into that here in a little bit. So here we go. Okay, before talking about the specific inferences, I want to start with a discussion of the difference between an inductive inference and a deductive inference. So chapters 6 and 7 were primarily about deductive inferences, and in particular whether or not the inference was valid. So when we talk about deductive arguments, at least the logic of deductive arguments, we're talking about whether or not the argument is valid. Now, with inductive arguments, uh, we have a different word for sort of the good logic, and that's strength. So where we want a deductively sort of valid argument in the case of deductions, we want an inductively strong argument in the case of inductions. So remember that with a valid argument, the premises of a valid argument are such that if the premises are true, the conclusion sort of has to be true, right? So there is uh, a relationship of necessity between the truth of the premises and the truth of the conclusion. Strong arguments, on the other hand, have premises that don't guarantee the truth of the conclusion, but rather make the conclusion likely to be true. So it's more probabilistic, and you don't have the guarantee. So strong arguments, sort of by definition, are not valid, but they may be strong. Another sort of difference here is that validity, with the deductive arguments that we talked about, was a feature of the structure of the argument. So in some sense, we didn't have to know the content of what was being said, rather just the structure of what's being said. So for instance, a modus ponens argument, which has as a premise a conditional, and then the antecedent of that conditional is another premise. Um, as long as those two premises are true, regardless of what the antecedent is or what the conditional is, if those two premises are true, the consequent of that conditional will always be true. So you know that the argument is valid without sort of knowing the content. Um, so with inductive arguments, though, that's not going to happen. That we're going to be talking about the structure of inductive arguments, but it's the case that both the weak versions of the argument and the strong versions of the argument will actually sort of share the same structure. So if we're talking about an argument by analogy, for instance, the good analogies look like the bad analogies, at least sort of structurally, and you have to sort of look at the content of what's being said in order to do the evaluation. So as we sort of go forward here, we'll be talking about the structure a little bit, but when it comes to evaluation, we'll be talking about sort of something else. Okay, so there are four inferences that we're going to discuss in this slideshow. The first is statistical syllogism. The second is enumerative induction, sometimes called inductive generalization or generalizing from a sample. With statistical syllogism, we usually say that we're going from sort of general premises to a more specific conclusion. With enumerative inductions or generalizing from a sample, the direction is reversed. We're going from sort of more specific premises or data to a more general conclusion. The third example is argument by analogy. So people who make arguments by analogy are not really going from the specific to the general or from the general to the specific. It's more specific to specific or general to general. Um, and then finally, we're going to talk about inference to the best explanation. And in the context of chapter 8, we're going to be talking about causal correlations. So inference to the best explanation is covered in a lot more detail in chapters 9 and 10, but the inference is a helpful tool in thinking about causal explanations. So you'll kind of see how that sort of plays out here in a little bit. Okay, statistical syllogism. This one's probably one of the easier ones. Structure-wise, most statistical syllogisms start with a statistic. This is the general premise I was talking about earlier. So some percent of A's are B's. Then you go on to say that some individual X is a member of A, and then the conclusion is that X is a B. So basically, these arguments are weak or strong just depending on the percentage. So if I say 90% of Democrats hate freedom and Donald Trump is a Democrat, therefore Donald Trump hates freedom, this argument would be strong, which means that if those two premises are true, which hopefully you believe that they're not true, but if those two premises are true, then the conclusion is probably true. So the logic just depends on that percentage. So if the percentage is low, right, if the percentage is less than 50%, then the argument will be weak. So in this case, we have 10% of Republicans worship Satan. Tim Hansel is a Republican, therefore Tim Hansel worships Satan. So again, the premises aren't true, but even if they were, the conclusion wouldn't even be likely to be true. You'd only have a 10% chance of being right, and that means the argument is weak. So these are pretty straightforward. Evaluation is just a matter of taking a look at that percentage. If things can get weird, I guess it would be in the area where you don't actually have a number, but just sort of a word. So words like most and almost all and nearly ever and things like that indicate that the argument is probably strong, whereas words like some don't really sort of tell you much. So those are some things to think about when evaluating statistical syllogisms. But like I said, the structure is pretty straightforward. Okay, enumerative inductions. These are the generalizations, and this is where evaluating things gets a little bit more complicated. So in general, the structure of an enumerative induction or a generalization is to start off with a premise that says something along the lines of some percentage of some sample population has the property P. So it's, again, starting with a statistic, but in this case, the statistic is more specific than the conclusion. So the conclusion will always be something sort of more general. So from that statistic, from that sample, we generalize to say that that percentage or somewhere near that percentage of a more general target population also has that property. So when it comes to evaluating these things, there's essentially sort of two things that we're going to talk about, and it has to do with the samples. So when we look at these things, we look at the sample population, and we say, okay, well, is the sample size sort of big enough? And then secondly, is the sample sort of representative? So with sample size, the rule of thumb is that, the bigger the sample, the stronger the inference is going to be. And then the representativeness of the sample, if it's not biased, if it provides a relatively sort of good snapshot of the whole, then that will strengthen the argument. So for example, opinion polls or scientific polling data that's run well will tend to be sort of relatively strong. So for example, I have some arguments here about sort of the coronavirus, and if you really want to know what percentage of in this case, Dane County residents have coronavirus, you'd probably do that through sampling, and the best kind of sampling is random selection. So in this case, we have 2,000 randomly selected sort of Dane County residents, and we test them for coronavirus, and we find that sort of 5% of that sample sort of comes back positive. So here we have a sample that's relatively large, statistically speaking. The size of Dane County is about 500,000 people, so it seems like a small percentage of the whole, but if it's randomly selected, then it's a relatively good size. And again, if it's randomly selected, then you have some reason to believe that it's representative. So from that sample, we could sort of generalize that around 5% of the entire Dane County community has the coronavirus. So this is an example of a pretty good uh, generalization. And that can go wrong in a couple of ways. One way is that your sample is too small. We've discussed this in chapter 5. This is the hasty generalization fallacy. So suppose we randomly select only 2 people from Dane County, test them for coronavirus, and neither of them have it. In that case, 0% of the sample population has the property P, and then the conclusion would be that 0% of the target population, everyone in Dane County has that property. So this is weak because the sample size is too small. You need a much bigger sample size to run these kinds of generalizations. Another problem which we haven't discussed is a sample that is biased or isn't representative of the whole. So for example, we might bias our sample by only testing people who have gone to the doctor's office with symptoms. So suppose we only test people, which is pretty much what we're doing, people who are symptomatic, and we come to find out that 50% of the tests come back positive. So that's a pretty biased sample. Again, you're only testing people with symptoms, and so you have some good reason to think that that is going to be much higher than the total population. So in this case, 50% of the total population, inferring that 50% of the total population has the virus is probably pretty weak based on this data. So again, when evaluating these things, the 2 things you want to think about are the sample size and the representativeness of the sample. Okay, analogical induction or arguments by analogy. The basic structure of these things involves usually comparing sort of 2 things. You start off, or somewhere in the argument, you say that A and B are sort of similar in a number of ways, that they share some properties. I have just sort of listed here P1 through Pn, however many are sort of listed, are what you need to use. And then usually then there's a property or an attribute that is of interest that we're sort of arguing about, and I'm going to call this I. So you say that there's a known property that one of them has, and then based on those sort of similarities, and A having this sort of further property of interest, the conclusion is that B probably has it as well. So the more similar that A and B are, the stronger this is going to be. So again, the good ones and the bad ones share the same structure. So in evaluating these things, we look at, or we think about, the relevant sort of similarities and dissimilarities between sort of A and B. So if there are some relevant similarities, or if the similarities mentioned are relevant to the attribute of interest, then that's going to strengthen the argument. And then if there are any dissimilarities, things that are different about A and B that are relevant to the attribute of interest, then that will sort of weaken the argument. So to talk about this, we're actually going to start with a weak argument. This is something that I got from page 278 of chapter 8. So the example on that page is pretty weak. Here we have humans and robots being compared, that humans and robots can both move about, that they can solve mathematical equations and win chess games. Those things are shared properties of humans and robots. And of course, the attribute of interest in this argument is the ability to feel pain. So in this case, humans have the ability to feel pain. That is a known property. We know that. And then the inference is that robots can feel pain. So this argument fits the analogical induction structure. It is an argument by analogy, but it's problematic in part because the similarities mentioned are kind of irrelevant to whether or not you can sort of feel pain. So irrelevant similarities don't do any work, right? You want relevant similarities. And then similarly, there seem to be a lot of relevant dissimilarities between sort of humans and robots. So for example, humans have a central nervous system and pain receptors, for instance, and robots don't, right? So robots sort of lack the anatomical structures that we tend to associate with the ability to feel pain. All right, so to see a strong version of this, we'd have to be comparing sort of human beings with something that's a little bit more sort of relevantly sort of similar. So in my ethics class, we talk about the moral rights of animals, and for some people, they believe that the animals have moral rights due to their capacity to suffer, their capacity to feel pain. Um, and we believe that we believe that dogs can feel pain, primarily because of their similarities with human beings, which we know can feel pain. So, for instance, we know that with humans and dogs, they share the anatomical structures that we associate with having pain, right? This would be a relevant similarity in that humans and dogs are mammals with a complex central nervous system, right? That we have brains and nerve endings and all kinds of things which we associate with the capacity to feel pain. So humans have it, and so do dogs. It's also the case that just behaviorally, we act similarly to painful stimuli. So we practice sort of avoidance behavior. When we're damaged, if we damage a leg, we limp. We cry out in pain if we're burned or stabbed or whatever. So again, sort of similar attributes here between sort of humans and dogs, attributes that seem to be sort of relevantly similar to the attribute of interest here, which is the capacity to feel pain. So we know that humans can feel pain, so we assume that dogs can feel pain too. So this is a strong argument because it seems like in this case, the similarities are relevant to the attribute of interest. And if there are dissimilarities, and there are, it does not clear which of any would be sort of relevant to this question. So are there any relevant dissimilarities? Maybe not. And in the absence of that, that does not weaken our argument. Okay, the final inference that you're going to be reading about is inference to the best explanation. Um, and this is actually discussed in chapter 9, so maybe you won't be reading about it, but I'll help you along here. So, inference of the best explanation has a pretty straightforward structure. Essentially, it deals with sort of explanations for some phenomenon. So, you have some phenomenon and various explanations, sort of competing explanations for that phenomenon. And if you have some reason to believe that one of these explanations is better than its competitors, than sort of all other explanations, then we infer through this inference that that explanation, the best explanation, so E sub B, B for best, is probably true, or at the very least more likely than others to be true. And evaluation of this is difficult. So, you have whole chapters devoted to sort of talking about how you think about or make explicit what it means for an explanation to be sort of better than others. But we're not really going to sort of get into that other than, just to kind of make sort of judgment calls as to be aware of sort of competing explanations and think about how we might sort of judge one explanation as sort of better than the other. So what is in chapter 8 is, or I should say, correlations. Correlations are relationships between sort of variables. So I have some examples here of sort of variables that are correlated with each other. Um, so smoking is correlated with cancer. Domestic violence is correlated with the Packers losing a game. And I should say domestic violence in Wisconsin is correlated with Packers losing a game. And ice cream sales are correlated with drownings. So these are all what we call sort of positive linear correlations, which is to say, as the rate of one increases, so does the rate of the other in sort of a linear fashion. So the rates of smoking are positively correlated with cancer. If smoking goes up, so does cancer. Similarly, domestic violence and Packers losses. If domestic violence goes up, so does the Packer losses. And then similarly with ice cream sales, when ice cream sales go up, so do drownings. So those are all correlations. And in chapter 8, there's discussion of this Mills method, the Mills method of concomitant variation, or concomitant. I never know how to pronounce it correctly. Uh, and the view is that, well, if there is a linear correlation, then there's probably some sort of causal relationship sort of going on. Um, but the nature of that relationship is hard to pin down because there are multiple different causal explanations for any given sort of correlation. And this is where sort of inference of the best explanation comes in. If it's possible, or if we have reason to think that one explanation is superior to the others, then we have some reason to think that inference of the explanation is true. Excuse me, I'm sorry. Then we have some reason to think that that explanation is true. So what are some possible explanations for correlations, right? When we get a correlation, we know that A is linearly correlated with B. We have a number of possibilities. One is that changes in A are actually causing the changes in B, so that A is causing B in a simplistic way. So that's one possible explanation, but there are others, right? Another possible explanation is that B is causing A, right? The changes in B are what's causing the changes in A. So we might be in a situation of reverse causation. A third possibility is that the A and B are actually sort of causally independent, that changes in A or changes in B aren't causing each other to change, but there's some hidden variable that's causing the changes in both, right? That there's a variable that we would refer to as a common cause that's causing the changes in both A and B. And then finally, I'll just sort of throw this in here. With any sort of correlation, it's entirely possible that it's just a fluke, that numbers sometimes line up in a way that statistically there is a correlation, but there's actually sort of no causal relationship between the two things. That's always something we have to keep in mind as a possibility. So when we think about inference of the best explanation, then what we need to do is consider these explanations and ask ourselves if we have some reason to prefer one over the others, right? Is one of these explanations sort of really best compared to its competitors? And if we have some reason to think that it is, one explanation does sort of rise above the others, then we have some reason to believe that it's true. So here are some examples. So we've already sort of mentioned sort of some of these, but here are sort of 4 examples of things where I think one explanation for each is superior than the others. So let's start with the smoking being sort of correlated with lung cancer. I think this is probably a pretty good example of A causing B. So it really is sort of the smoking that's causing the lung cancer. That's because it's pretty, the other explanations are pretty implausible in comparison. So to say that it's the lung cancer causing the smoking, uh, while that's possible in sort of some situations, it's usually temporally just all wrong, right? It's usually that the smoking comes first, and then comes the cancer. Uh, and assuming that we can't sort of cause something backwards through time, that's not going to work. People have disputed the possibility of sort of a common cause that may be sort of if smoking doesn't cause cancer, it'd be most likely some common cause, but we haven't sort of figured out what that is. So we don't really have a good candidate for that right now. And then finally, the accidental correlation doesn't seem likely, just given that we've just done a lot of studies and there's a lot of data out there that shows this correlation. So it keeps on sort of coming up. So very unlikely that it's just sort of a fluke of the numbers. So for that reason, sort of E1 is sort of the best explanation. So E1 is most likely true, right? Smoking causes cancer. All right, what about this domestic violence and Packer losses? You know, is domestic violence causing the Packers to lose? That's probably not true. What's more probably the likely explanation here is that the Packer losses are causing the uptick in domestic violence. So when the Packers lose, Packer fans who are drunk and angry turn to their spouses to vent that anger, and that's probably what's going on, is that the Packer loss is causing the uptick in domestic violence. So in that case, E2 would be the more likely explanation, right? That B is causing A. The Packer losses is causing domestic violence. All right, the ice cream sales correlation with drownings. That's most likely a common cause. It's not the case that ice cream sales are causing people to drown. Ice cream is causing people to drown, or that drowning is causing people to buy ice cream. It's most likely that there's some sort of third thing that is explaining that correlation, something that is causing A and B to sort of go up or down, independent of each other. So the most likely sort of culprit here would be warm weather. So as the weather gets warmer, more people are going to be eating ice cream, and more people are going to be swimming, which will raise the likelihood of people sort of drowning. So as warm weather goes up, so do those two things. As the weather cools, those things will go down. So the correlation is caused by a common element. All right, finally, there it is entirely possible that the correlation is entirely accidental. And I have this example that I came across a few years ago of just sort of one study that was trying to do some scientific research on the power of prayer. And they were trying to do this sort of scientifically sort of controlled study where they had patients who were recovering from heart surgery, and they were looking at their sort of rate of death. And with these patients, they had one group that they had some people sort of praying for them, and another group that they weren't praying for them, and they were trying to sort of see if they would get any sort of data. And it turns out that they did. They had a statistically significant sort of correlation between the people who were prayed for and the people who died, and it was positive. Which is to say that if you were in the prayed for group, you were more likely to die, so not make it through your heart surgery, and that raised some eyebrows in some people, because obviously one possibility is that getting prayed for causes you to die, and it couldn't have been the other way around because the praying came before the death, and so it seemed a bit sort of wonky, but chances are that in this situation, it was just an accident of the numbers. That with replication, you would expect that that effect would go away, and indeed, it has. That anyone who's tried to study the power of prayer in this way, uh, by having sort of official prayers for somebody, usually finds just no correlation. So there's no correlation typically between sort of being prayed for and surviving your surgery. So there you have it. You have inference of the best explanation in the context of correlations. So there are typically sort of four possible explanations. If you can eliminate all but one, then you have some reason to think that that explanation is true. So as we sort of go forward here, then what you will be looking at are various examples of these four types of correlation, and you will be asked to sort of identify them. So what type are you dealing with? And then using what we've sort of discussed, talk about whether or not you think that the inference is strong or weak. And in most cases, the inferences will be problematic. There will be something about those inferences that will weaken the argument, and it'll just be up to you to sort of figure that out and explain what's problematic about it.